Hello, this is Dallin here with Developer Insight, and today we're going to be continuing our walk through the Elixir guide, covering basic types in this chapter. That's going to include integers, floats, booleans, atoms, and symbols, strings, lists, and tuples. So we'll go ahead and get started by opening up our interactive Elixir console, or interactive Elixir in the console, with the IEX command. And we can start off with some simple division. 10 divided by 2. A couple things to notice here is that returns to you a float. That means that if we do 12 divided by 5, you'll see that it'll give us a floating point number, and that's by default. If you want to do a hard cut division, an integer division, you can do that with the divide function. And you'll see that we just pass in the two arguments, and that's doing 10 divided by 2. And you can see it gives us an integer answer here. Now, one thing that I'll just throw in here is that Elixir actually doesn't require parentheses. You can just run divide 10, 2, and that works just fine. Although among the Elixir community, it is preferred to put the parentheses there. I'll also mention for people who are familiar with other functional programming languages, it is common in other languages to just have the two parameters passed behind it, and that actually does not. That was a syntax error in Elixir, so you do need the comma between parameters, and it does only work if you have more than one parameter to not include the parentheses. Another useful function is the remainder function, which will get the modulo or modulus answer, or it'll just give you the remainder of the division, whichever way you want to define that. So for inputting numbers, we can actually do it for binary, octal, and hexadecimal. They have shortcuts for that. They all start with 0, so we can just do 0 binary and then throw in a binary number, and there it is. Or we can do 0 with octal, and that allows us to input octal numbers. And lastly, we have hexadecimal, which is just a 0 and an X, and that allows us to input hexadecimal numbers into the console. Or I guess just right into the language. We can also convert floats to integers, and we can do that in two ways, using the round or the trunc function. So the round is doing exactly what you'd think it is. It's going to round the number to the closest integer, which in this case 3.58 is 4. But now truncate, that's going to drop off the decimal, and so if we do the same number, it's just going to leave us with the integer 3. Next, we'll move on to Boolean values, and this will be written simply as true and false. And in order to check that, Elixir has a lot of built-in functions to check the types. So we can just type in is Boolean here, and it'll tell us. But then if we do a number, it'll obviously come back false. They have a lot of these functions, so for example, if we want to check if something is an integer, or if we want to check if it's a float, let's just do an actual integer, and that'll come back as false because it needs to have a decimal. And we can even do a more generic one like is number, and that's going to work for both integers and floats. The next type we're going to be going over is atoms, and atoms are a constant whose value is its own name. And some other languages might call these symbols, but it's basically where, if we have apple, that is the value in and of itself. These are most often used to express like state in the Elixir language a lot. So for example, if we call a function, it might return to us OK, and so we know from that value that the function succeeded, or it might return error. And it allows us to just quickly check to see if that's the case. And so you can do a simple, if it's okay, oh goodness, then that's going to come back true. Booleans are actually atoms also, so we can check that with if true is equal to the atom true, it's going to come back true because they're actually the exact same thing. True, false, and nil, those three atoms do not need the colon in front of them. You can just define them directly in the language, so they're kind of the exception there. And we can check that with our is functions again, with is atom, And we get another one with is boolean as well. There we go. So you can see that the atom false is also considered a boolean. Now, strings in Elixir are wrapped in double quotes, and they're encoded in UTF-8. So as you can see, there we go. We've made our first string. And in order to do string interpolation, we can assign it to a variable, and then we can insert it into the other string with a hash, curly brace, and then the name of the string. There we go, and it goes ahead and it combines it to hello world. We could do that same thing with the atom. So if we change stir to actually just be the colon, let's say there, and then we ran the same command, it would change it to hello there. So atoms will act as strings when you print them out. Within your program, when you go to print out to the console, you can use the function io.puts, and that's going to print out to the console. One thing to notice with this function is that it actually returns the OK atom, and that's showing you that it was successful, and it would return the error atom otherwise. Strings are represented internally as binaries, and binaries are a contiguous sequence of bytes within memory. So we can prove that with an isBinary function. And that's going to go ahead and return true for us. And this next thing I'm going to include because I think it's useful, but we can, so for example, if we go to do byte size, and that's just going to return to us how many bytes each string takes up. I'm going to copy paste this here to address Unicode characters. So there we have a Unicode character. When I go to run that, on Windows particularly, it's actually going to throw a Unicode conversion error, and that's just because it's not supported in this terminal. And so I'm going to exit out and just run the IEX with the whirl flag. By doing that, it's going to open up a separate terminal with Erlang. And so now if we go to run that same function, it's going to work correctly. There we go. And it tells us that it's 6. And as you can tell, 1, 2, 3, 4, 5. There's 5 characters per se here. But because this is in Unicode, that actually takes up 2 bytes. And so our byte size is actually 6. So if we want to get the correct count as far as the length of a string, we're going to want to use the string.length function. And that'll properly count the graphemes instead of just the bytes. The string module has a lot of really useful functions in it. For example, upcase. And that's just going to do exactly what you'd think it would do. Make the string uppercase. The next type that we're going to be covering are linked lists. And the way to do a linked list is with square brackets. So you just put the values inside the square brackets with commas in between. And there we go. And you can actually mix types inside of these. So we can just put 1, 2 true, and then let's do 3.2 here at the end. And so you can see that they can be mixed up as much as you want inside a list. And in order to get the length of this, so let's just do a 1, 2, 3 list. And there we go, it'll return to us the length. In order to concatenate linked lists, you can just use the ++ operator, or the append operator, whatever you want to call it. So do ++ and then 3, 4. And you can see that that's been appended to the end. And it works the exact same way to subtract from it. One thing to note here is that I subtracted true and false from it. And you can notice that it ignored the 1 and the 2, and it just took the first true and false it could find. And so you can see it ignored this last true when subtracting that type there. One thing to note while adding and subtracting from these linked lists is that data structures in Elixir are immutable. And what that means is that if we have a list 1, 2, and we're going to go ahead and name that to first list. And let's say we want to add 3 and 4 to this. So if we do first, plus plus, and then 3, 4. It looks like it worked, but if we print out first here, you see that it hasn't changed. That's because, as we stated earlier, it's immutable. First isn't going to change on its own. So in order to properly do that, we have to capture the value returned from that append function. And the way that you do this is you need to assign the result to something. So we can just set first equal to first and 3, 4. And so now if we print out first, you can see that it actually has changed because we've assigned the variable to the new linked list that has been created. And that's something that's really important to recognize, is that it is a new linked list. Every time you add, append, take away, it's going to produce a new value. It's not actually modifying the original value stored in that variable. Now, a data structure is a form of storing data in memory in a structure that allows you to access it more quickly or in an organized manner. So, for example, a linked list, which is what we're using here, is a data structure in which there is a node, and that has the data stored inside of it, along with a pointer that points to the next node. And at the end of that list of between data with the pointer, when data to the pointer, and when it gets to the end and there's no more nodes, it's just going to be pointing to nil, which means that it's just the end of the list. So now we understand how a linked list works. Some of these other functions are going to make a little bit more sense. So let's go ahead and define a list here. And what we can do is we can look at the head of the list, which is going to be the value inside the first node. So you can see it returns to us 1. And then if we look at the tail, that's actually going to be printing out the pointer that's pointing to the rest of the list. So as you can see, that the tail is 2, 3, because that's the value that's is looking at the next nodes that are following that head. And so we actually, in order to access them, we need to iterate through one at a time in order to get to where we want to go within the linked list. If we do an empty list, so if we try to get the head of an empty list here, that will give us an error because there's nothing there. We have no nodes to go and look at. Another thing to recognize is that if we have a list of integers here, that's actually going to print it out as hello. And that's because those numbers are all valid ASCII characters or ASCII numbers. And if we want to get the type of that, we can actually use I. And I is going to tell us that that is a list of integers that is printed as a sequence of characters, or ASCII characters. Yeah, it's a list, and it's a collection of numbers that can be printed as characters. One thing to recognize is that it has single quotes here. Now these single quotes, those show that it's talking about a list of individual numbers or ASCII character codes. And that is not the same as the double quotes, which show a string, which are more graphemes. This is referring to integers that represent characters here. And I'm going to prove that real quick for you by just doing hello is equal to the string hello. So we've got that ASCII character string versus the normal string value. Let's go ahead and return to us false because they are not the same thing. Those are two different types. The next basic type we're going to talk about is a tuple. And a tuple is really similar to a linked list in the fact that it stores different types and values in a, I guess, somewhat list of a thing. But it's a tuple. So it's a curly brace, and then you can store any type. So we'll just store OK and hello. There we go. There's our first tuple. And the big difference between the linked list and the tuple is that the tuple stores its values contiguously in memory. And this means that it's going to be really fast to access an element by index or get the tuple size. That makes it a very quick operation. And we can show you how to grab a value in a tuple. So we'll go ahead and save that same tuple we made previously. So there we go, now it's stored in a value named tuple. And let's go ahead and access an element of it with the lm function. We're going to pass the tuple in there, and then what index we want to grab. So that'll be, we'll grab index 1. That's going to return to us hello. And we can get the tuple size with, you guessed it, tuple size. And then in order to add something to the tuple, and remember that data structures are immutable in Elixir. And so for this case, it's going to be put element function with tuple where we want to put it. So we'll put it in location 1 and world. And because it's immutable, this is going to return a value. This is not going to modify the value that's stored inside the tuple variable right now. And so as you can see, the hello has changed to world. But if we go ahead and print out tuple, you'll see it's still hello. It hasn't actually changed. That's just the value that returned from that function. So now the big question is when to use the list versus the tuples. But it all comes down to use case, because they both have their benefits. So for the list, you have to think back to what we talked about earlier about what is a linked list. Okay, it's different nodes that have a data value, and then they have pointers that point to the next node. And so what that means is that it's really fast to insert new elements, because all you have to do to insert a new element is create a new node in memory, allocate memory for a new node, put the data in the node, and then just have the previous pointer point to this node. And so it's just one small allocation and then redirecting a pointer. And so it's very fast inserting elements to the front, but then when it comes to, for example, appending an element to the end of the list, that can be a little slower because that speed depends on the length of the list. Each time you need to add to the end of it, you need to get access to that end pointer. And so what that means is that you gotta go all the way through the list, bouncing from node to node to node till you get to the last one, so that you can get a hold of that pointer and point it to the new allocated node. Whereas if you're putting the new node in index that's closer towards the front, it'll be pretty quick. Particularly if it's in the front, that's going to be very fast. So that makes it very slow to check the length of the linked list, as well as appending to the end. And now the tuple, that's contiguous in memory. What that means is that all of the values inside of the tuple are stored right next to each other in memory. And so all we need to do, if you ask for a specific index or a specific element to grab, it's just going to calculate, okay, it's 3 memory locations over from the beginning because it's in the 3rd index or whatever it is. And it makes it very quick because it just calculates and then grabs that memory location. But then it's very expensive to update or add elements because since it's an immutable, tuples are immutable, it's going to reallocate the whole tuple again. So if that tuple is pretty large, it's going to have to reallocate a whole thing in memory just to change that one value. And so that's where the drawbacks of the tuple come in, but Elixir actually has a little bit of a fix for this. And it's lying a little bit by saying that because they do allow tuples to share memory. What that means is that if they have the same values in the same location, the tuples are actually just going to point to the same tuple in memory, the same contiguous memory. And there's going to be pointers pointing to the same location. So Elixir does try to help you out and try to make that a bit better. Tuples are used regularly throughout Elixir to return constant values like the status of a function as well as the returned value of the function. And an example of this is the file.read function. So we can go ahead and try file.read, and I actually already made a test file here, so we'll just go ahead and grab that one. When we read that, you'll see that it returns OK as the first value of the tuple, and then the hello world, the text that's inside that file. And one of the benefits of using a tuple here is that we're only going to be accessing those first and second index, just be grabbing those. We're not going to be mutating this at all, and it's just, there's no reason to follow pointers throughout memory when there's just going to be 2 values right next to each other. You just need to grab them quickly and check them and get them. And so that's one example, but then if we look here with the file.read and we look for some other file that doesn't exist, you'll see that it'll then return the error atom and the ennuent. I don't even know how to pronounce that, but it's just something that it's just an error code that goes back to C that means error, no entry, or it just means that the file doesn't exist. And so that's an example of how tuples are used regularly throughout the Elixir language to quickly give a status of the function, or to return the error, or to return the value associated with it. Elixir is going to help guide you to which structure is better. An example of that is the lm function that we used earlier, we can, with the tuples, this function, with the one, make a quick tuple in here, and then we'll access the first index of it. So that function only exists for tuples. There is no function in list to go grab a specific item. And a common rule is that if a function is named size, then it's in constant time, which means it's pre-calculated and it's very fast. Whereas if a function is named length, then it's linear, and it gets slower with size. And so that's why the linked lists have the length function to figure out how long it is, because it actually has to real-time go through the whole thing and find how long it is. Whereas the size function for the tuple is pre-calculated and it's very fast. One way to remember that is that length and linear start with L. And so when there's a function called length, that means that it's linear time and it's going to take a little bit longer depending on the size. So examples of this that we've used thus far are tuple size, byte size, length, and string.length, which tells you the number of graphemes. All of those will kind of guide you, okay, size, that's fast, length, that's kind of slower. The final basic type we're going to be talking about is functions. And functions in Elixir are identified by their name and arity. And arity is the number of arguments that the function takes. To grab the docs for a function, you can just use the h function. So for example, use h, trunk, and then you type the arity, which just takes 1. And I'll go ahead and explain it to you. Okay, it returns the integer part of a number, and it gives you some examples. And trunk is in the kernel module, and that's why it's available in this namespace. If you could also refer to it as kernel.trunk, and that's really where it's defined. This also works for operators, so you can do kernel.plus, and that takes 2 arguments. And then you'll go ahead and show you this, the arithmetic addition operator. Now, Elixir also supports anonymous functions, which are exactly what they sound like, functions that don't have names. And so we'll do an example here. Add equals a function that takes 2 arguments, and that adds them together. And we'll go ahead and end there. And in order to call anonymous functions, they have a special dot notation. So we'll call add, and then give it 2 arguments with that dot in between. That's going to give us 3, because it's running our function. And Elixir makes that a very clear line there between named functions and anonymous functions. An example of why is that, let's say we go ahead and make a new function named trunk. It takes 1 value, and it just returns that value. And it lets us do that. And so now if we call trunk, just like we were using before, 3.24, it still truncates it, gives us the correct answer. But now if we do the trunk with the dot, 3.24, it's going to be calling our anonymous function. And it's just going to be returning the same number without making any changes to it. So it's very important that it makes that distinction between anonymous functions and named functions, where the anonymous functions are just assigned to a variable that may be of the same name of an existing function. There is a simple boolean for checking if something is a function, and it's exactly what you'd think it would be, is function, and what do you know, it's true. And we can actually add another argument to that, where is truncate with the arity behind it, and that will also return true, as that function does exist. One rule with anonymous functions is that they can access variables in the same scope. And so, for example, if we do double, and we run add inside of it, it's totally okay with that. And it's allowed to access that add function that we defined above. Variables within a function, however, are scoped. So, for example, if we have an x variable, we set that equal to the integer 42, and then we define an anonymous function where we change the value of x to 0, and then we call that function, we'll see that x is still the same value. It's still 42. So that is the end of this video. I really appreciate you watching, and I'll look forward to seeing you in the next one.